Hi, this is Dave Johnson with another edition of Math Off Topics. In a recent video, I derived the Lagrange trigonometric identity for cosine series, which I used to find the uh, definite integral of cosine of x dx without knowing its antiderivative by using a Riemann sum. So in this video, what I want to do is derive the Lagrange trigonometric identity for the sine series, which could be used for similar purposes. So let's get into it. So I've gone ahead and written the Lagrange trigonometric identity for the sine series. Notice here's the finite series. K here is the index of the sum. And you can see that the result of doing this gives you a closed form expression, which is handy when you want to replace the series with a closed form expression. And when you take the limit, say in a Riemann sum, as n goes to infinity, this becomes an infinite series. So it becomes a little unwieldy, and having something like this actually is very beneficial. So how do you derive something like this? Well, I think you start with the sine theta. We're going to complexify it using the Euler identity. And I'm not talking here about how we come up with this identity. It's pretty often talked about, even as in pre-calculus courses, and certainly by the time you get to differential equations, you've seen this expression. So sine theta is equal to e to the I theta minus e to the negative I theta divided by 2i, where theta I is the square root of -1, so it's the imaginary unit. And first thing I want to do is I want to replace theta with k theta, because we need that. So sine k theta is equal to e to the I k theta minus e to the negative I k theta divided by 2i. Now I'm going to sum both sides. And why are we doing that? Well, because we want to derive something that's equivalent to this left side. And so if we can sum the sine k theta and go through the algebra and get that expression, that's what we want to do. So I'm going to write summation k equals 1 to n of sine k theta is equal to, now I'm going to go ahead and distribute the sum. And I'm going to first pull out the 1 over 2i just to make things a little easier. So then this becomes sum k equals 1 to n of e to the I k theta minus sum k equals 1 to n of e to the negative I k theta. Now, if you look at these summations, you can recognize that they are actually examples of the geometric series. And we did pretty much the same thing in the other video. So let me remind you. So if we have a common ratio r, sum as k goes from, let's say, 1 to n of r to the k, then we can rewrite this as r times 1 minus r to the n divided by 1 minus r. Now this result is written in different ways by different textbooks, but they all boil down to the same expression, the same formula. So I'm going to go ahead and plug in what we know. And let me go ahead and call this whole thing S. I like to have a handle for, in this case, S represents the sum. So S is equal to, and then 1 over 2i. And so I can replace this first sum, because this is e to the I theta. And let me go ahead and say r, in this case, r is e to the I theta. And for the second sum, it'll be e to the negative I theta, but I don't need to write that. And so I get r, which is e to the I theta, times 1 minus r to the n, which is e to the I n theta, all divided by 1 minus e to the I theta, and then minus, and that sum can be replaced with that r, which is e to the negative I theta, so e to the negative I theta, times 1 minus r to the n, which is e to the negative I n theta, divide by 1 minus r, which is 1 minus e to the negative I theta, close parenthesis. Okay, so now the problem is we got this denominator and this denominator, and they're not quite the same. And rather than multiplying them together and simplifying and so on, there's a trick which can be used. So if I multiply top and bottom of this expression by e to the negative 1/2 I theta, and top and bottom of this expression by e to the positive 1/2 I theta, I can turn them into basically the same thing downstairs. So let me go ahead and do that. So equals 1 over 2i, and then e to the negative 1/2 I theta times e to the I theta times 1 minus e to the I n theta, divide by, and then downstairs, e to the negative 1/2 I theta times 1 minus e to the I theta, minus, and then upstairs, e to the positive 1/2 I theta times e to the negative I theta times 1 minus e to the negative I n theta, all divided by 1 minus e to the negative I theta. Okay. Now, if you watch my other video, you'll understand why I did this, but I'll go ahead and explain it again here. So let's go ahead and just multiply in the denominator and see what happens, and also simplify in the numerator. So we get 1 over 2i times, we'll do the numerator first. So multiply that all out. We get e to the 1/2 I theta minus, and then e to the, now watch what happens. Here's an n, and this is when you multiply these together, you get, or when you add the exponents, you multiply these two factors together, you add the exponents, and you get positive 1/2 I theta, but you add that to the n, you get I times n plus 1/2 times theta. And downstairs, we get e to the negative 1/2 I theta minus e to the positive 1/2 I theta. And then the next term, we do the same thing. We get a slightly different result, but we can write that down. So e to the negative 1/2 I theta minus, and then again, we've got this n here, which when you add it to this, you get e to the negative I times n plus 1/2 theta. And then downstairs, you're going to have, oops, forgot to write the e to the 1/2 I theta. And so you'll get e to the 1/2 I theta minus e to the negative 1/2 I theta. Okay, now we got to watch this here. This is the negative of this, and I'd rather have the positive coefficient in the first term. So I'm going to factor out a negative sign from here, and I'm going to move that negative sign up into the denominator, or the numerator. So I get 1 over 2i And now applying the negative sign in the numerator, I'm going to rewrite it, change the order, e to the I n plus 1/2 theta minus e to the 1/2 I theta. And I'm going to go ahead and write the, go ahead and distribute the minus sign upstairs in the second term, and I get so plus e to the negative I times n plus 1/2 theta minus e to the negative 1/2 I theta. And downstairs we have the common denominator, which is the e to the 1/2 I theta minus e to the negative 1/2 I theta. Now I'm going to combine the numerators, change the order, and it'll be more obvious what's going on. So equals 1 over 2I times e to the I n plus 1/2 theta plus e to the negative I n plus 1/2 theta. So combining the terms that involve the n and the exponent, plus, so minus actually, e to the 1/2 I theta, and go ahead and factor out that minus sign again. I guess I didn't need to distribute it. Plus e to the negative 1/2 I theta. And then downstairs, we still have our same denominator, e to the 1/2 I theta minus e to the negative 1/2 I theta. So what I want to do now is look at these. This, when you have a plus sign here, this looks very much like a cosine. And this also looks very much like a cosine, but this looks like a sine. We're just missing the denominator. So if I divide this by 2, and I divide this by 2, and I divide this by 2I, then we're going to get closer to what we want. And so let me go ahead and do that. Now, you may say, well, I can't just arbitrarily do that. But yes, I can, because if I come back and fix it in the same step, then that would be legal. So let me write this 1 over 2I. And then now upstairs, we're going to have e to the I n plus 1/2 theta plus e to the negative I times n plus 1/2 times theta. And I'm going to go ahead and divide this by 2. And I'll make this all good in a moment. And then minus, and then e to the 1/2 I theta plus e to the negative 1/2 I theta, and divide that by 2, okay? And then downstairs, we've got our e to the 1/2 I theta minus e to the negative 1/2 I theta. And because that looks like a sine, I actually want a 2I down here, okay? Now, you might say, well, wait, it isn't finished. It's not correct. Well, you're right, it's not. So this 2 and this 2 and this 2 will cancel. So I didn't do anything. I just put 2's there, but if I canceled them, I'd be back to where I started, except for this I. And if I put a 1 over I, let's do that out here. So times 1 over I. Now, this I is in the numerator of the denominator, and this I here that I added is in the denominator of the denominator. So now these i's would cancel, returning us back to where we were up here. But now this is all correct. Now one more little step is this I times this I is -1. And so basically what has happened is I've introduced a -1 here. And what I can do now is I can just multiply that -1 times this numerator, just change the order. And so this gives, so 1 over, the i's gone now. So I get 1 over 2 times, and then I'm going to write this term first. What is that? Well, it's a cosine of 1/2 theta, and then minus, and then this term, which is cosine of n plus 1/2 times theta, and then divide by the sine of 1/2 theta. And if I go ahead and multiply by that 2 inside the parentheses, what we end up with is cosine 1/2 theta minus cosine of n plus 1/2 theta divided by 2 sine 1/2 theta. And that's exactly what we wanted. So let's go back to the very beginning. Notice, so cosine 1/2 theta minus cosine n plus 1/2 theta divided by 2 sine 1/2 theta. And that's exactly what we wanted. So let me shrink this down so you can get a better view of it, perhaps. And that's it. So I hope you've enjoyed this video. If so, please like and subscribe, and I will see you in the next video.